Okay, welcome back. Second part of this lecture. We have reached section 4.4.2, where we will define an Ito process. So we will give a formula for an Ito process here, an Ito process which we denote by X. It is based on the Ito integral. And with this Ito process, we will look at its quadratic variation, and we will also define the stochastic integral with respect to that Ito process. So that will be the contents of this section 4.4.2. So let's get started. So in order to define the Ito process, let W be a Brownian motion, as we usually define it, Wt, t greater equal to 0, with a filtration script f of t, t greater equal to 0. So that is our basis, our common usual basis. Then the Ito process itself, the Ito process we denote by X, as I mentioned, so it's X, X of t, t greater equal to 0. That is now a process of the following form. X of t is written down as x0 plus the integral from 0 to t delta u dwu plus an integral from 0 to t theta u du. So here we see the Ito integral appearing. And we have x0, we have this process here with the stochastic integral, and we have another regular integral here, an integral over the time axis dt, right? du, in fact. And in detail, this delta t, t greater equal to 0, as well as theta t, t greater equal to 0, these are adapted processes adapted to the filtration ft, t greater equal to 0. So we can benefit from all the properties of an adaptive process. So you can see here, this is a slight generalization of the process that we have seen before. We have augmented the process from before with this term. In fact, this is seen as an Ito integral. In fact, an Ito integral, which in this case defines the so-called Ito process. Well, we need conditions for things to hold true. If we define the process on the basis of simple processes, again, one of the conditions is that the expected value of the integral from 0 to t of delta square u du is finite. So that is one of the conditions, a finite variance. And the other one is that theta t, the function theta t, that is Riemann integrable, right? And moreover, we require x0 to be non-random, to be a constant. So x0 a constant, two processes adapted to the filtration, the Brownian motion, and the technical conditions for properties to hold true. So let's work with this process. And in differential form, it is more easily remembered, understood. If we take x0 to the left-hand side, we see dx appearing in differential form, dx. And dx is then written as delta t dwt plus theta t dt. And this is a form that we will often encounter. And why is this form so convenient? Well, first of all, remember that this is just another way of writing this integral formulation, but all the computation rules, the calculation rules that apply to the differential form, they also hold, they can be verified for the integral form. And it's so easy to do computations in the differential form. Think of dw being dt, etc., etc. The formal way is via the integral formulation, but it is very practical and handy to work with the differential formulation. Try to remember this differential formulation. It's an important one for the Ito process, and we will often encounter it. Try to remember this form in differential notation. dxt is delta t dwt plus theta t dt. It has a dt part, and it has a dw part, a combination of a dt part and a dw part in the right-hand side. And now we will work with this formulation. And the first thing we will do is let's look at the quadratic variation. And so we have now a different process, the Ito process, and let's look at the quadratic variation of the Ito process. And for this, we have a lemma. And the lemma is for the Ito process. The Ito process is once more written here, xt, and we write it out one more time in order for you to remember it. It's x0 plus the integral from 0 to t, delta u dw plus the integral from 0 to t, theta u du, and t is greater or equal to 0. That is the Ito process, and the quadratic variation is given by this. So we write it in the standard way. The quadratic variation of x, of t, is the quadratic variation of x from 0 to t, and that is by definition, or that is given by the integral from 0 to t of delta square u dt. And we can prove that. And of course, we can also write this in differential form. Let's first do that. In differential form, the quadratic variation would be the following, based on the lemma. The lemma says then dxt is equal to, well, the differential form square. So the differential form delta t dwt plus theta t dt times, one more time this, delta t dwt plus theta t dt. And we can do this multiplication. The first term times the first term times the second term here times the first term, and the last terms all together. And if we do that, we see the following. It's delta square t dwt. So we recognize again something which we know how to handle. Then the cross term, 2 times delta t theta t dwt dt. So we see this cross variation popping up. And the last two terms make delta square t dt dt. And we know what to do with this. So we have our ways to deal with the term dwt. We know that dwt dt is equal to 0, in fact, and the same holds true for dt dt. So if we take it one step further, we see that this is nothing but the first term. The other terms are 0. The first term, delta square t dt, and where this is equal to dt. This term is 0, this term is equal to 0. So in fact, we see that it's easy to show in differential form that dxt is equal to delta square t dt, and that implies in integral form that the quadratic variation of x of t is the integral from 0 to t from delta square u du. All right, let's prove it. And in order to prove it, we simplify the notation. So we take two shorthand notations for this integral from 0 to t delta u dwu. We write that down as it, as we know it. And the second integral from 0 to t theta u du, we denote it by rt. And if we have that, then you know that xt is equal to x0 plus it plus rt. Yes, xt is x0 plus it plus rt. Now, if we look at the quadratic variation, then what we need to do is, again, we take a partition. Yeah, we take a partition of the time interval from 0 to t, and we partition in n parts, a partition script p sub n parts, where t0 is equal to 0, tn is equal to t, and we have a sequence t0 is less than t1 up until tn. Now, on this partition, we can write our quadratic variation as follows. It is a sum I runs from 0 to n minus 1 of the increments of the Ito process, x at ti plus 1 minus xt squared. And if we write this in this way, and we know that we are dealing with this form here, then this can be written as, the x0 will cancel out. So this can be written as I ti plus 1 minus it squared. So this one squared. The second one squared the increments of r. The sum I runs from 0 to n minus 1. R at time point ti plus 1 minus r at time point ti squared. Plus 2 times the mixed term. Plus 2 times the sum I runs from 0 to n minus 1 times I at ti plus 1 minus I at ti times r at ti plus 1 minus r at ti. Now letting this partition, the mesh width, the maximum mesh width in this partition go to 0, the number of points go to infinity. So we have multiple points, and the space in between is getting to 0. Then we find the following. So the first term, the sum I runs from 0 to n minus 1 of this squared difference of the I term. And the I term, remember, the I term is this, that we have seen before, right? That is the quadratic variation. So when this partition, the mesh width in this partition tends to 0, then this first term will convert to the quadratic variation of I. That is the integral from 0 to t delta square u du. In fact, that is already the answer that we want to achieve. So the first term already gives us the answer, which means that the second and the third terms, they should both be 0. So let's look at that in detail. The second term, so the sum I runs from 0 to n minus 1, r ti plus 1 minus rti in absolute value square. Well, we can bound that. By taking one of these out. These are continuous functions on a compact interval. So we can take the maximum out, and we do that here. We can take the maximum out of one of these terms. So then we have a less or equal. We take one out, and the maximum for one I between 0 and n minus 1, we take it out. In absolute value, r at ti plus 1 minus rti. And then we have this sum remaining, the sum of one of these terms. The sum I runs from 0 to n minus 1 of these increments of r. Now, these increments of r, we can just write out. That is, in fact, by definition, the integral from ti to ti plus 1 of theta u du in absolute value. Yeah, so, and that is multiplied by this. And then we have these absolute value signs here. We can take the absolute value inside the integral, and then again we have a less or equal sign. So that is less or equal. The maximum of these distances are ti plus 1 minus rti in absolute value times the sum I runs from 0 to n minus 1, the integral from ti to ti plus 1 of the absolute value of theta u du. Now this, in fact, the sum of these thetas, that is our definition when the mesh width goes to 0, when n goes to infinity. That is a finite integral, the integral from 0 to t of theta u in absolute value du. And it is multiplied, when n goes to infinity, it's multiplied by something, the distance which goes to 0. So it's 0 times a finite integral, and that is equal to 0. So the second term is indeed equal to 0, something that we desire. And the third term also goes to 0 because it's the mixed, the mixed term. And if we look at the cross variation, so when the mesh width goes to 0, so when n goes to infinity and therefore the mesh width goes to 0 of this term, 2 times the sum I runs from 0 to n minus 1, I at t, I plus 1 minus I at ti times r at ti plus 1 minus r at ti. Again, we take out one of these parts, namely the I. We take out the I. The maximum of the I, we take it out of the sum. And then, of course, we need a less or equal sign here. And what remains is this sum. I runs from 0 to n minus 1, the integral from ti to ti plus 1 theta u du. And by similar reasoning, we let the mesh width go to 0. This will go to 0, this first part. The second part is in fact a finite integral, a well-defined integral. This term is finite, and in total, this one goes to 0. The second one is finite. In total, this is also equal to 0. So the third term also goes to 0. And in fact, we have proven that the quadratic variation of x is indeed the integral from 0 to t delta square u du, where x is the Ito process defined as xt is x0 plus the integral from 0 to t delta u dwu plus the integral from 0 to t theta u du. And in other words, in differential form, dxt is equal to delta square t dt. Yeah, that is easy to remember. The expression in differential form is easy to remember, and by that you can also immediately remember the quadratic variation form. Okay, let's define now an integral with respect to an Ito process. And before we had the stochastic integral with respect to Brownian motion, and now we will generalize this to define a stochastic integral with respect to an Ito process. So before, remember, we had our Brownian motion, Wt, t greater equal to 0, and that gave us the notion of the stochastic integral as follows, the integral from 0 to t, delta u dwu, t greater equal to 0, where delta u greater equal to 0 was an adapted process, adapted to the filtration of the Brownian motion. And we needed the technical condition, the expectation of the integral from 0 to t of delta square u du had to be finite. That was the situation before, and now in this section, we will define the stochastic integral with respect to the Ito process x. So now let x be our Ito process, just defined, x0 plus the integral from 0 to t, delta u dwu, plus an integral from 0 to t theta u du. Let that be our Ito process. And now in this case, again, let's not forget the differential notation of this. Dx is equal to delta t dwt plus theta t dt. And a dt term plus a dw term, not only a dw term, but we have a dt term added to it, to the Ito process. Now we will have another process, gamma t greater equal to 0. Let that be a process which is adapted to the filtration of the underlying Brownian motion, script f t greater equal to 0, of the underlying Brownian motion. And then we define the integral of gamma, gamma t greater equal to 0, with respect to the Ito process x, t greater equal to 0 as follows. And now the integral from 0 to t, gamma u dxu. So here you see the integral with respect to the Ito process, gamma u dxu. That is now defined as the integral from 0 to t, gamma u delta u dwu, plus the integral from 0 to t, gamma u theta u du. So in fact, what we do, if you look at the definition, so here you see the definition in differential notation, the definition of the Ito process, we substitute, basically, we substitute this in the definition in order to get the integral. So dx is replaced by delta t dwt, which is in this term, plus theta t dt, which is in this term. And that defines the integral of gamma with respect to the Ito process x. All right. So how about the Ito-Doeblin formula for the Ito process? How does that then look? And this goes essentially with the same idea as in the proof of the Ito-Doeblin formula for the Ito integral with respect to the Brownian motion W. So we have the following generalization here for the Ito process x. Now let x t greater or equal to 0 be the Ito process. Again, dx t is delta t dwt plus theta t dt. And let f, a function of t and x, be a function with continuously differentiable first and second partial derivatives. Yeah, so this is the setting where the only thing changed is that we're now dealing with an Ito process. Then, for any time capital T larger or equal to 0, we have the following expression. F, a function of t and xt, of capital F of capital T and x capital T, is equal to f of 0 x0 plus the integral from 0 to capital T df dt and df dt with arguments t and xt dt plus the integral from 0 to t df dx of t and xt dxt plus 1/2 the integral from 0 to t, the second derivative of f with respect to x at t xt dxt dxt. So this is the generalization of the Ito-Doeblin formula when we are dealing with an Ito process. So we are encountering dxt here, dxt here. And these, of course, for those we can use the substitution of the differential form, dxt equal to delta t dwt plus theta t dt. So let's do that. And let's use, moreover, let's use the fact that we have just found that dxt dxt, that is equal to delta square t dt, the form that we have just found in the previous slides here, right? Related to the quadratic variation of the Ito process, dxt is equal to delta square t dt. Let's use that. And when using that and substituting for dx this here and dxt using this expression related to the quadratic variation, we end up with the following form. F of t and xt is equal to f of 0 and x0 plus the integral from 0 to t df dt t xt dt. And now we substitute for dx the two terms here. So we get two integrals, in fact. The integral from 0 to capital T df dx at txt times delta t dwt plus another of these, the integral from 0 to t df dx at txt theta t dt. So again, here you see this term and this term together, they make this term. Yeah, where dxt is just replaced, substituted. The Ito process is just substituted. And the other term here, there we substitute for dxt, we substitute our form that relates to the quadratic variation delta square t dt. So here we have plus 1/2 the integral from 0 to t, the second derivative of f with respect to x at txt times delta square t dt. So this one is the Ito-Doeblin formula for the Ito process written out. The first version here is maybe easier to remember with the dx term and the dxt term. And then we need to substitute all the details that we know, the differential form for the Ito process and the quadratic variation related term, we substitute those, and then we end up with Ito-Doeblin's formula for the Ito process. Now, how to prove it? We will be brief because it goes essentially the same as before. First I do a remark, sorry. So first we do a remark. What we will say here is if the function f does not depend on t, when it's only a function of x, then the above lemma reduces, gets a more simplified form. It reduces to the following form. F, which depends on x of t, is f on x of 0, the integral from 0 to t, df dx, dw, plus the integral from 0 to t, df dx times theta t dt, plus 1/2 the integral from 0 to t, the second derivative of f with respect to x, times delta square t dt. So the df dt term disappears, as you can imagine, right? So when the function doesn't depend on t, we will not have any derivatives, first derivatives with respect to t. So the proof is essentially the same for Ito integrals as we had it before. We use Taylor's formula in 2 dimensions. So the idea of the proof, we only sketch the idea. It goes essentially the same as before the break. So we take a partition of our time interval 0 capital T. T0 is 0, it's less than T1, less than T2, less than T3, less than T4, up to Tn is equal to T. And then we, on each of these intervals, we look at the difference ft xt minus f0 x0. And we look at it as a telescoping sum again. It's a sum I runs from 0 to n minus 1 of f at time point ti plus 1 x ti plus 1 minus f at ti x ti. And this is just a telescoping sum, which is essentially, which is indeed identical. And the first term and the last term remain. And now for each of these terms, we can apply the Taylor expansion, the 2-dimensional Taylor expansion. So for each of these terms, we have df dt at ti xti times the time increment ti plus 1 minus ti. And we add to that df dx times x at ti plus 1 minus x at ti. Then the next term in the Taylor expansion enters, plus 1/2 the second derivative of f with respect to x times the distance x ti plus 1 minus ti square. And then, so that is in the x direction, then we get it in the t direction, plus 1/2 the second derivative of f with respect to t times the distance in the t dimension square, ti plus 1 minus ti square, plus the mixed term, 2 times the 1/2 of the mixed term makes the mixed term the mixed derivative df dx dt times ti plus 1 minus ti times xti plus 1 minus xti, plus any higher order terms that will converge to 0 when n tends to infinity. Now, again, we recognize several terms here. We recognize the time derivative here, and we recognize, so we call that E1, I1. I2 is the first derivative with respect to x. I3, the first derivative with respect to x squared. I4 is the derivative, the second derivative with respect to time. And I5 is the mixed term. Well, you can imagine when n goes to infinity, the first term will turn to, the sum will turn to an integral, ft dt. Here we will see something like the first derivative times dx appearing. Here we will see something when n goes to infinity and the mesh width goes to 0, like a second derivative times the square increments. The square increments go with dt. Here we will see something with dt squared, and dt squared goes to 0. And here we will see something like the cross variation, and the cross variation will also turn to 0. So we see that on the next page. Remember, I1 is our term with the first derivative with respect to t, I2 the first derivative with respect to x, I3 the second derivative with respect to x, I4 second derivative with respect to t, and I5 the mixed one. So I1, when n turns to infinity, when n goes to infinity, we can make this go to we can make this converge to an integral from 0 to t of df dt at t xt dt. The second one, when n goes to infinity, that will be the integral from 0 to t df dx at t xt dxt. The third one, when n goes to infinity, for the third one we make use of this formula, dx dx is equal to delta square t dt, and therefore this will give us 1/2 the second derivative with respect to x at t xt times delta square times dt. I missed the delta square here, I think, right? Times delta square times dt. Here is the delta square. So it will be on the slides. You see there can be a mistake once in a while in the slides. So the delta square should enter there. So here must be a delta square. And the fourth term with the dt squared goes to 0, and the fifth term as well. For this Ito-Doeblin's formula for the Ito process. And we outlined the proof. Again, here, please see delta square t dt, and that comes from this quadratic variation differential. So this concludes today's lecture. Thank you for your attention.